In this lesson, we're going to be looking at our output request management. So this lesson is going to be a little bit different to previous ones because I'm going to use some visual aids to help understand what the problem is before we jump in and have a look at the code. So you might have already spotted this as we've gone through sequence diagrams and through our code for managing sequences. But essentially what we need to do is manage more than one sequence requesting one asset to perform a task. But we don't necessarily always want to stop the sequence in order to allow another one to take over, such as the filling sequence and the wash sequence, not interrupting the filtration sequence in order to operate AVO1, the inlet valve. So if we have a look at our output command for a valve in its most simplistic form, we have here a software valve asset. That is our manager, the UDTs, everything that goes with a valve. And typically what we do is give it a command to open. That gets passed to our manager and the logic that's associated with that manager. And that generates a physical output command to our output card, which then interfaces with the physical valve asset out in the field. The valve moves and feeds back a signal back to our input layer, which ends up in the valve asset or the manager, and we then read it moved and is now in the correct position. But let's take a look at what happens if we have more than one point of origin for our manager when it comes to requesting a valve to move. So in this example, we have three sequences, sequence 1, 2, and 3. All of them can ask for this valve to open. We can't have all three sequences write to the same software variable that's used in this valve asset to say open, because if we're using ladder or structured text, we could end up in the situation where sequence 1 is asking it to open, but sequence 3 is still scanned by the logic, even if it's not in use, and sets that variable back to false, in which case sequence 1 can no longer tell this valve to open because it's scanned first. So sequence 3 always wins. So the way around that is to have an interface in which sequence 1, 2, and 3 all interface with a dedicated management system before we get to the actual software valve asset or the manager for the valve. So this is where our request handler comes in. And what this request handler does is allows us to effectively OR all of the sequence requests. So sequence 1, 2, and 3 can all be making a request, or we could have any combination or none. And the request handler will interpret that by amalgamating all of those signals into one common signal that says, I need you to open the valve to the software, the valve asset. You also have the opportunity then to include the interlocks into the request handler. So there might be times where we say, or it gives us the opportunity to be able to do this, that sequence 1 is running or sequence 2 or 3 is running. We are making a request to the valve to open, but some other factor that is external to the sequence prevents that valve from opening. And although the sequence is requesting that valve to open, we no longer want that valve to open because of a particular interlock. So we therefore remove the request post sequence. So the sequence is still saying, I want you to open, but at this layer here in the interlocks, we're saying, ignore that request, it's no longer valid. Now, remember that you do need to be careful of checks. If the sequence is continuously checking, is the valve open, then the sequence may fail. But remember that our managers take the requested value or the requested commands to open the valve and then check that the valve is in that position all the time. We get a discrepancy fault if it's not in the position it's supposed to be in. And because this request handler will no longer be saying open the valve, it's okay for the valve to shut and the valve will not register a discrepancy even though sequence 1 is asking for it to open, because the valve manager never actually sees that request from sequence 1. You can take this one step further as well. Well, you can take it as far as you want it to go, really. But here's an example of sequence 1 also containing its own subsequence. And not only can sequence 1 control this valve, but the subsequence can also make requests to control this valve. Now, there may be conditions or certain scenarios when you're writing software that subsequences are active and can run, but they interrupt the main sequence without causing the main sequence to restart. So, if you give an example, if you're running from steps 1 to 100, and every 5 seconds a subsequence runs and opens a valve for a few seconds, you don't want sequence 1 to have to stop to do that, but your subsequence must still have control over the valve, even if sequence 1 also opens that valve at particular times during its steps. So you have a request handler sat in every sequence as well, and that allows us to have more than one element of that sequence being able to request a valve to open without affecting the common output from that sequence that ends up at this level here, requesting for the valve to open. Now, that might not make much sense right now, but we do have an example of this in our software. So we'll jump over to the software now and have a look at how this all sort of comes together. So let's have a look at our filter sequence manager. And the first thing to notice is that we have two outputs from this sequence that directly interact with assets. So this filter sequence manager is capable of opening AVO1 and also interacting with and opening MVO2. So if we have a look at where these are used, we'll notice that they come out of our filtration request handler. Now, this filtration request handler only accepts one type of input, and that is our request structure. So UDT filtration requests. And if we have a look at this in our interface and have a look at what we're able to do with this, this has a different amount of interactions for each asset. So AVO1 has two. It has the AVO1 fill mode open request, and it also has a standard AVO1 open request. And we can cross-reference these and jump to where they're used. So we can see that the fill mode open request comes from the fill sequence, whereas the open request comes from a coil in the start filtration step. The same with MVO2, this one only has one, and it again comes from the start filtration step. And we also have an internal structure as part of the request that is relative to shutdown. So in here we have an AVO1 close request and an MVO2 close request. And we can see that these are used as part of the filtration shutdown sequence. So when the filter needs to shut down, we interrupt the main sequence. We don't tell the sequence to do anything because remember our shutdown management is all handled up here. We simply say we are shutting down. That comes down to our shutdown sequence to say we're shutting down either by normal or fault, and then the requests to close those valves are enabled. And if we have a look in the filtration request handler at how that's translated into interacting with the open command, we'll see that the open command can come from either the fill mode or the normal sequence, as long as the shutdown close request is not active. If the close request comes in, then we kill the open command, and AVO1 is a spring return, so as soon as it loses its open command, it would return under spring to closed. So we don't need to tell it to close, we just need to tell it to no longer be open. And the same thing happens with MVO2. If MVO2 is being asked to move, then it moves to its predetermined position. Remember that MVO2 is an actuated valve. It's a it's not an open close, it's a modulating valve. So all we're doing is saying we want you to open. We determine elsewhere what that position is. This is just the command to say to the PID controller, or however this particular valve is controlled, you need to do something now as per your external controls. And the same thing happens there. If that's told to shut down, then we no longer give that command. So that's a very basic internal request handler. We just simply take multiple requests and turn them into a singular output command. If we look at the wash sequence, which is written in SCL, and have a look at the outputs, these are all statuses here, but you'll notice here we have AV01 open command, O3 open command, O4, O5, MV06, which is our outlet valve, modulating outlet valve, start position command, and then the PID control command for the outlet valve as well. And again, if I cross-reference where these are used, they end up on a wash request handler, where the input is requests, which is UDT wash requests, and then they interface with our outputs coming from this request handler in order to set the command. So if we have a look at where requests is used, you can see it's used in multiple different places, all through the different steps that we have. And if I come and have a look at the static for requests here, you can see that, again, we have a very similar setup where we have multiple things for different valves. So AV01 fill again, AV01 top wash, AV03 backflush, AV04 air scour, AV05 drain down, and also AV05 wash open. And then we have the start position and PID control for MV06. So not too dissimilar to the actual command outputs. And again, we have shutdown, but in this particular case, if we ever shut down the wash sequence, we simply close all valves. Because if we're in the middle of a wash and something goes wrong, we're going to close all the valves. If we are at the end of a wash cycle and about to go into filtration, well, we want to shut all the valves before we go into filtration anyway. And if we're shutting down off the back of a manual push button to start the wash sequence, then we want to close all the valves because we're no longer going to be doing anything at the end of the cycle. So the shutdown in this sense is very, very simplistic. If we go into the request handling function and have a look at how this one interfaces, we'll see that it does nearly exactly the same, or it does do exactly the same as the filtration one. So we have our ORD commands here, or ORD requests. As long as we're not asking all valves to close, then AV01 opens. AV03, AV04, and so on until all the valves are controlled. The difference with MV06 is we produce two outputs because there are two different ways in which this one can be controlled. It's moved to its start position for a predetermined time or until it reaches that start position, and then we enable PID control. So this one's handled slightly differently. The key to the request handling is that you understand that you can modify the signal in these areas here. So this side to the left is what's coming from our sequence, or whatever our controlling aspect of this asset is. Whatever's making the request for an asset to do something is all on the left here. And then all on the right is our now command to actually say this sequence or this process wants to do something with this asset. What we're giving ourselves here is an opportunity to modify the behavior. So I can add in an additional signal here if I want to. I could add in a timer if this request handler was a function block. I could add in a pulse, a counter. You could do whatever you need to do in order to manage that signal without affecting your upstream logic, which is the sequence in this case. And that gives you a great degree of flexibility when it comes to standardizing sequences and processes, but changing the outcome depending on what type of asset you're using downstream. And you'll notice that that's a common thing throughout this architecture, because we can do that in our input mapping layer. We can now do it in our request handling layer, and you can also do it in the output mapping layer when we actually get to send the physical signal to our assets in order to get them to do something. We have another opportunity at that level as well to manipulate our signals. So that covers the sequences, but once they come out of the sequences, they then need to be processed again because we have more than one sequence. And if you remember rightly, we have the opportunity where the filter sequence can be running. It gets to a particular point where it checks do I need to wash before I start? And if that answer is yes, then it calls the wash sequence manager to start via this interlock here, which is wash sequence requested from filter. Now that means that I know it won't be happening yet, that the filtration sequence won't be asking AV01 to open because we're already paused at that section of the code in order to run this. But there could be the opportunity where we end up with both the wash sequence and the filtration sequence being able to control AV01. And certainly if this code was much more complex, you could end up in that position. So you'll notice that when we come out of filter sequence manager here, AV01 open command comes onto a command filtration sequence AV01 open command, which is a temporary because we're in an OB. OBs can't have static. So we're in a temporary here. And if we have a look at what this command structure has, it has an internal structure for filtration sequence, which has AV01 open command, MV02 enable command. And then we have our wash sequence, which also has AV01 open command, and then the other associated valves for the wash sequence. And if we look at where this stuff is used, you'll notice that it's on the output interface of our sequences. Again, down here are the open commands for the wash sequence. And you'll also notice that MV06 doesn't fall onto this because MV06 is a special case and goes to an interlock, so the interlock can then interface with the PID to get the PID to either be in manual mode at its start position or to operate correctly for its flow meter control. And we'll cover that in the examples when we get to the actual running of this filter. In a sort of live demonstration, you'll see how the PID stuff comes together then. If I come down here, we now have the output command handler, which I appreciate was not on the diagrams that I showed you earlier, but this is the additional layer that allows multiple sequences to come together. So what we have here is the AV01 open command and AV01 open command from the filtration system and the wash sequence. And then there's nothing else interacting with any of the other valves at this moment except for the wash sequence. When it comes to MV06, if either of these interlocks are active, then MV06 has its enable command. And then if you cast your mind back a little bit to our device control lesson, there where we looked at the device control layer, we'll notice that the device control layer is now plugged in to this output command handler. And if we go in and have a look, at this point here is where we interface with our asset management data sets. So AV01 open command links in with our device control layer, AV01 auto enable, same for MV02, same for AV03. For all of them, it's a straight turn on the auto enable. Our asset manager is now auto enabled. And if we have a look at where this is used, so AV01 auto enable, if we come to our devices section and have a look at the manager for AV01, we can see that we have our asset data coming in here. Control data is coming from device control layer typed AV01. And if we just jump in the block and have a quick look at the auto enable coming from the control data, we'll be able to see that that effectively opens the valve. So control data, auto enable. If you're auto enable and you're in auto mode and your open mode is 0, which means that we are normally closed, then is it normally closed? Sorry. Yeah, sorry, 0 open on enable, 0 open on auto enable, spring close return. So we'd be in mode 0, then turn on the asset data IO output open request. And it's that then interfaces with our output layer. Very sort of complicated to just visualize in your mind. So if you need to go back and watch this video again, or even jot it down as you go through the video and sort of draw it out, then by all means do so, and of course ask questions. if you get stuck with visualizing how this goes together. But what we're doing is building standard interfaces, but having degrees of flexibility by having these sort of areas that are standard interfaces, but not standard objects in terms of they're not in the library as a typed object that can't be edited. They are in the library as a master so that they can have the right interface or an updatable interface, but the logic inside can be manipulated, added to, modified, changed without affecting the rest of our standard control objects, such as sequence control loops and management of assets, such as this object here. And hopefully you can visualize how easy it is to add additional functionality then to open a valve or to close a valve, like putting something here that says you're not allowed to run this. You're not allowed to open AVO1 for the first, 5 minutes of a sequence starting on one particular job. So you might have 40 of these out in the field, but this one, for whatever reason, something to do with that particular site, is not allowed to open that valve for the first 5 minutes. Well, that's quite easy to do now because we can add that here, or add it here, or we can go in and add it in our the request handler inside the filtration sequence. But if the filtration sequence was standardized, locked, version controlled, and revisioned in our library, we still have an element that we can add it here, and it would, or here rather, we could put it there, and it would be specific only to the filtration sequence and only on this job. But the version number for our filtration sequence has not changed and is the same as every other job that we've done. And it's trying to think of things in that mindset where we think of things like control objects are still an asset to us, and the valve obviously is an asset in its own right. And what we're doing is standardizing how they talk together, standardizing the logic in which they use to operate, but having that flexibility through request handling to modify the behavior of that asset based on project dependent requirements. So I hope I've explained that properly. And if I haven't, or if you need a bit more help, drop a comment, find me on LinkedIn, and we'll go from there.